Good morning, everybody. I'd like to thank Barbara for inviting me to this workshop. It's really nice to be part of this meeting and see all the various presentations over these 2 days. And so what I'll do is I'll summarize some of the work we've been doing over the last 10, 12 years or so on trying to understand what controls continental rift and passive margin formation, the various styles, possibly some implications for the degree of magmatism. And most recently, we've focused on the role of the Mantle lithosphere and its ability to become mobile during rift and passive margin formation. And so a lot of the work has been done in collaboration with Chris Beaumont in Halifax, Romanowicz more recently, and other postdocs and PhDs. And so what I'll do is I'll briefly review some observations that indicate very contrasting styles of non-volcanic rifted margin formation. And then I'll basically introduce you to 2 end members, one which we call type 1, narrow non-volcanic rifted margins, and another type which we coined type 2, wide rifted margins. And I'll show you that the main controlling factor on these 2 end members is the rheology of the crust and its strength. And then in the last part of the talk, I'll introduce the effect of the lower lithosphere and its ability to become mobile and actually flow in the opposite direction as rifting is occurring. And so it will flow towards the rift axis, as you will see. And so here, one very well-known system, the Red Sea Gulf Aden-Afar triangle. In the Red Sea, we have a typical example of a very narrow rift. Extension is localized over a width of about 100 to 150 kilometers, and we classify this as narrow because the width is about the thickness of the lithosphere. And so it's a very efficient localizing rift system. We do not really know if this is symmetric or asymmetric, but it's definitely very narrow. Now, if we go to an other end member, the basin and range, then this is actually still, it didn't manage to break up, and it's on the other end of the spectrum. It's extremely wide. Extension has not been very efficient in localizing deformation, and we see extensional faulting over an area that's about 800 to 1,000 kilometers wide. So we have multiple horsts and grabens and very distributed extension. Now, I'll go on to introduce you to the forward numerical models. I'm using a 2-dimensional and actually also 3-dimensional, but I don't have time to show you 3-dimensional models today. 2-dimensional thermomechanical model. It solves for both frictional plastic and thermally activated nonlinear viscous rheologies. The extensional domain, the model domain, includes a crust mantle lithosphere and also a sublithospheric mantle that extends until 600 kilometers. And we need the mantle to deal both properly with isostasy, but also with the thermal evolution. The continental crustal system is seeded with a very small weak spot, but this is actually providing a very minor control on the style of rift and passive margin formation. And the model is basically extended by kinematic boundary conditions here on the top. And since the total model domain doesn't change its size, we need a very small amount of influx of material in the sublithospheric mantle here. But since the mantle is weak, the sublithospheric mantle is weak, this doesn't actually have any effect on lithosphere deformation. I can comment later on the strength paradox, because these models actually do have a total integrated strength of a lithosphere that is within plate boundary forces, and that's because we're using wet, or at least implied, hydrated frictional rheologies, and that's a very simple solution to the strength paradox. But we can discuss that later. For most of the models, I will show you a zoom of the central model domain, because this is where most of the action is taking place. And so this is a domain that's about 400 kilometers wide, and the thickness of the lithosphere and a bit of the sublithospheric mantle. Right, so one of the issues that we encountered when we started looking at what proper rheology to use is that we compiled a lot of flow laws for crystal rheologies here for wet quartz, viscosity as a function of temperature. And we see that the various flow laws gives us an enormous range. And so this illustrates the uncertainty that's associated with crystal rheology. So we effectively actually do not know the strength of the crust very well. And so we have taken the liberty in our forward models to explore this variation in crystal strength in our models. So we've taken a very simple approach. We've just taken one flow law, and here are typical strength versus depth distributions for the crust, mantle lithosphere system. And we have taken a very simple approach where we take one flow law and we scale this up and down to test and explore the sensitivity to crystal strength. And so for the very strong end member, strong crust end member, the crust is actually almost completely brittle. And we only get terminally activated creep in the top of the mantle lithosphere at about 50 to 60 kilometer depth, depending on temperature and strain rate. And here we basically have our typical strength decrease. Now in the other end member here on the right side, we allow the mid and lower crust to be very weak. And so here we can see that we actually have two strong layers, an upper crust and an upper mantle lithosphere, and those are effectively decoupled. And in the middle here I have something in between that allows for partial decoupling between the upper frictional crust and the frictional and strong upper mantle lithosphere. And so as you will see, this very simple one parameter variation results in a very large variation in style. And so that's shown here. Here are three models run for about the same amount of extension. And we see that in this very strong middle and lower crust case, we have major detachments that cut through the crust mantle lithosphere system, and they cause very large-scale asymmetry, allowing for this purple material, which is lower mantle lithosphere, to be exhumed to the seafloor. And the yellow here is a sublithospheric mantle. So just again, the upper crust, lower crust, upper mantle lithosphere, lower mantle lithosphere, and sublithospheric mantle here. If we allow for terminally activated creep in the middle and lower crust, we see that this tendency for large-scale asymmetry and detachments cutting through the crust and the mantle is broken. And that's because the shear zones, the frictional shear zones, they actually decouple, they detach in the weak middle and lower crust. And so we still have narrow extension, but decreased asymmetry and also decreased tendency for exhumation of the mantle to the seafloor. Now in the last case, here at the bottom, we included very weak middle and lower crust, and we see that the upper lithosphere and lower lithosphere, they're essentially exhibiting different drift modes. And so we see that the lower lithosphere here is localizing in a very narrow manner. It's actually completely ruptured, and the sublithospheric mantle is actually exposed to the base of the crust. And the crust itself is extending in a very wide and distributed drift mode. And so these three numerical models, the only parameter that's varied is the strength of the crust. So there's only one parameter that says a major control on style of extension. And they confirm these cartoons that have been around in the literature for a long time with basically very strong coupled systems leading to asymmetric, a bit weaker to more symmetric but still narrow, and very weak middle and lower crust leading to very wide crystal rifting, and in this case narrow mantle lithosphere rifting. All right, now again to some classical systems that have been studied a lot in the literature. Here's a summary of observations from the Iberian-Newfoundland system. And one of the key observations of this system is that it's magma-starved, and it shows, basically here we have the continental crust boundary on each side. And then it's exhibiting this large green domain, which exhumed mantle lithosphere that's now found at the seafloor. And only here in the middle, at M0, it has actually was able to create a mature mid-oceanic ridge system. And so how do we form and how do we create these large areas of exhumed mantle lithosphere? It's not sublithospheric mantle, the petrology shows that it's lithosphere, to the seafloor. A few more observations. We see that the conjugate crystal sections here, they show all very narrow rifted margin formation, very narrow crustal necks. The crust is thinned from its reference thickness to 0 over a width of about 50 to 100 kilometers. And so the final stage of rifting was really very narrow. And so one very simple conclusion we can make from this is that the crust broke before the mantle lithosphere. There have been, there's a whole community working on this particular rifted margin, and this is one example of a reconstruction by Romanowicz and his co-workers. So here's the reconstructed section at M0 with wide tracts of exhumed mantle at the seafloor, and here's a reconstruction back in time. Here on the right I have again a numerical model now in time, so with progressive extension from top to bottom. And we see that in this case the very strong mid and lower crust allows faults, shears, frictional plastic shear zones to cut through the crust into the mantle, and this allows the crust to neck and rupture in a very narrow rift style, and it also allows to exhume some mantle lithosphere. But I should say that the amount of mantle lithosphere that we're exhuming here to the seafloor is much less than that's what is observed, right? And so in between here, this is actually now creating an amagmatic zone here, but this is new sublithospheric mantle. And so we can, with detachment faults, exhume some mantle lithosphere to the seafloor, but merely not enough what's observed. All right, so here's an animation of the same numerical model. If it wants to run, yes. That shows the evolution a bit better. I can't use my pointer because it will stop the animation. Actually, there's another pointer. One interesting feature is that we have this black line, which is actually sea level, and we see that some parts of this system actually become subaerial during rifting. All right, now moving on to another system, the central South Atlantic conjugate margin system. This is a very interesting system because it exhibits a large variation in structural style of rifts along strike. We have actually a very magmatic segment here in the south, and we have a more amagmatic, very wide segment here, and we have oblique rifting here. And I'll mostly focus on this part over here, although the other parts are also very interesting. What is maybe useful and relevant to point out is that this is rifting partially a cratonic piece that extends from Africa to Brazil, Congo to San Francisco, and here it's rifting Pan-African orogenic crust, so presumably weaker crust. And so here's a conjugate section through this margin, from the Angolan margin to the Brazilian Espírito Santo margin. And one key characteristic that you can immediately pull out is that the continental crustal section is extremely wide. We're talking here about 350 to 400 kilometer wide rift with very thin crust, about 10 kilometer or less. There are a number of other observations that are also interesting. One of them is that we have early fault-bounded syn rift and then actually undeformed sag basins that accumulate actually quite a lot of sediments. And on top of this we have salt that is late syn rift early breakup, which presumably was at sea level and indicates very shallow water conditions. And this is actually a problem, an isostatic problem, because how do we get these highly thinned margins at sea level? They should actually be deep water. And so here's a number of key observations that need to be explained. How do we get this wide distributed thinning of the crust? There's a lack of apparent uppercrustal thinning. We have this undeformed sag and flat basement. We have very shallow water conditions and marine sediments and salt on highly thinned crust. From purely isostatic considerations, this should be deep water. And there is here a transitional domain, and it's maybe not so relevant now, but it also needs explanation. And so this is an example again of a model with very weak middle and lower crust. And so here again, we see that the middle, in the early stages of rifting, the lower lithosphere, the mantle lithosphere, localizes deformation quite efficiently, whereas the upper part, the crustal system, doesn't localize deformation and exhibits a very wide distributed rift style. At this stage here, the lower lithosphere is completely ruptured, and we're actually almost exposing the asthenosphere to the base of the crust. And one interesting feature is that the crust is now so weak that it's actually flowing towards the distal margin. It's maybe not very clear, but here in the middle we're actually piling up weak mid and lower crust, and it's basically flowing as a Poiseuille flow, as a pressure-driven flow, because the rift lengths here are higher than the ocean basin. Some of that weak material is actually pumped to the distal margin. Now, at this stage here, we have formed extreme wide distributed rifted margins. We actually accumulate sac basins, undeformed. There's actually sedimentation in these models now. And so they accommodate largely undeformed piles of sediments that are consistent with the sac sediments that we observe in these basins. All right, one other feature that's interesting to point out is that deformation is actually in substance, is actually diachronous. We have early deformation in the proximal parts of the section, and with time deformation migrates to the distal margin. And that's actually illustrated by these basement subsidence curves that show progressively later subsidence in the distal margin. All right, so another animation that may help illustrating the model behavior. And so again, we see the mantle lithosphere rupturing very efficiently, crustal extension being very wide and distributed and inefficient. We see actually sediments on top now occurring. Some of the middle and lower crust is piling up and pumped to the distal margin. Most of this system is very close to sea level. It's very shallow water conditions. And only after actually quite a large amount of extension does this system manage to break up. And it produces extreme wide rifted margin formation. And it's just by allowing the crust to be quite weak. All right, so now a picture showing some pictures that we've seen already quite a lot. So there's one ingredient that in these models that we found was not satisfactorily explained, and was that they, in some places in these basins in the Central South Atlantic, we need even more buoyancy. And in addition, there's evidence for lower lithosphere extending out below the margin, as I'll show you in a minute. And so we stumbled on a number of papers, including the one by Johan and Romanowicz, that argue that the lithosphere, the mantle lithosphere, is actually composed of two layers, a highly depleted upper lithosphere and a more mobile, possibly lower depleted lower layer. And so we decided that to include this type of layering in our forward models to see how they would behave. And so this is just to evidence that these layering exist. So there's other reasons that to argue for continental mantle in the oceanic mantle. And so there's petrology indicating that there is continental material in the shallow oceanic mantle in the oceanic, coming from oceanic basaltic lavas. And that's just another piece of evidence that there are continental fragments out there, and we need to explain them. And so here's another one. It's actually along the Cameroon line. There's evidence for continental mantle lithospheric and also lower crustal contamination of the volcanic lavas on the Cameroon line into the oceanic basin. And so we have to ask ourselves, well, how do we actually get this continental material there? All right, so here is a S-wave tomography image at between 100 and 175 kilometer depth by Beck et al. From the Griffin group. And it's basically showing a section through Africa and the Angolan margin here. And here's the same section in depth. And so what's actually very interesting is that we can image the root of the Congo craton, but we can also see that this velocity anomaly extends out into the oceanic basin. And it shouldn't be there. the edge of the continental crust is there, and the oceanic lithosphere presumably is new. So why and how do we get continental mantle lithosphere extending from the crotonic root into the oceanic basin? And of course, this has very important implications for magmatism and also for vertical motions, because depleted material is less likely to melt and it has a different density. It's lighter, and so therefore it should provide additional buoyancy. And so here's some more images by De Mackenzie and Keith Priestley showing the same type of basically lithospheric material extending into the oceanic, the margin and the oceanic basin. And so we designed a numerical model that was very similar to what we did before, but now it actually includes a crotonic area on the right side. And so here we have now strong crust because it's crotonic. We have highly depleted upper mantle lithosphere, lower depleted lower mantle lithosphere. It's still, it's very conservative in its depletion. It's only 17 kilograms per cube lighter than the nominal lithospheric mantle. And it's a bit weaker than the upper mantle lithosphere. And so here's an animation that shows what happens if we include this into these numerical models. And so what we see is that when these models extend, this light material actually preferentially flows into the necking area. Because it's depleted, it's a lower density, it actually prefers to flow in here, and it underplates these wide rifted margins, and it would therefore predict a lower degree of melting, and it would also add additional buoyancy. One other interesting thing to point out is that in the continental part, this also has implications. We have actually a layer there that's thinning, shearing, and it presumably is also adding heat to the continental lithosphere. And we're actually now investigating the consequences for topography and heat in the continental areas. We put this now together as for a model here on the top, including sediments with these very wide rifted margins underlain by depleted mantle lithosphere, and only at this stage does it actually manage to create a mature mid-oceanic ridge system. And we believe, at least we suggested, that this may explain some of the anomalous observations that are made in the central South Atlantic. Now, coming back to the very narrow cold volcanic margin systems such as Iberia and Newfoundland, I mentioned that we have difficulty explaining these very wide tracts of mantle lithosphere at the seafloor by detachment faulting. And so what we did now as well, we included, just to back this up by some more data, actually the same authors, De Mackenzie, Keith Priestley, argue for also mantle lithosphere extending out into the rifted margin here, where it becomes very non-volcanic in Nova Scotia and Newfoundland, here on the east coast of Canada. Other data from, actually again from the Sydney group, showing the same thing here. Apparently depleted material sticking out into the passive margin. Again here they argue that this yellow material is actually reworked mantle lithosphere. And so if we now include this mobile, effective mobile lower lithosphere in forward models that produce narrow rifted margins by making the crust strong, we observe that the crust again ruptures in a very narrow rift manner. We have some exhumation of mantle lithosphere, normal mantle lithosphere to the seafloor, but then again this mobile lower lithosphere flows into the necking area and creates a wide area of amagmatic, depleted lower mantle lithosphere. That may explain how we can obtain these wide areas of exhumed mantle lithosphere at the seafloor. Lastly, in these models, we only included this depleted, thicker root on one side, and this was motivated by the South Atlantic example, where we didn't have any good constraints to argue for such a route on the Brazilian side. We know that there is one below Congo. But of course, we may also argue that this depleted lower lithosphere extends all across the margin. And so here is just an example to illustrate that this behavior is also occurring if we have actually a depleted lower mantle lithosphere layer extending all the way on either side. And so this is actually initially fully stable, and when it starts rifting, it produces again narrow rifted margins. Thank you. Narrow rifted margins here on top, and it exhumes mantle lithosphere, lower depleted mantle lithosphere to the seafloor. And so we can summarize what we've seen in these various models. In these end member types, the style of crust mantle lithosphere extension in narrow wide rifting is largely controlled by the strength of the crust. Strong crust leads to very narrow rifted margins and exhumation of a small amount of mantle lithosphere to the seafloor. Weak middle and lower crust leads to these extreme wide rifted margins where the mantle lithosphere ruptures before the crust. And in this case, we have actually asthenosphere or new mantle lithosphere below the crust. If we include the effect of mobile lower lithosphere in these models, in type 1 strong crust cases, we can actually explain wide areas of exhumed mantle lithosphere to the seafloor. And in type 2, we would predict that these wide rifted margins may be underplated by this mobile lower depleted, possibly cratonic lithosphere. Right, so I've summarized also this in text, but I think I've explained this in the previous cartoons reasonably well. Now, since there's been quite a lot of discussion about magmatism today and yesterday, I thought I'd at least show you one case that includes magmatism, although it's not the main focus of this talk. I thought it might be interesting for some of you to see some of this. And so we know from melt relations that melting below mid-oceanic ridges happens in two stages. Basically, we have a first phase of damp melting where the damp solidus is crossed and a small amount of water in the system leads to small melt fractions from about 100, 120 kilometers to about 60 kilometers. And then below mid-oceanic ridges, we actually obtain a large degree of melting when the dry solidus is crossed is about 60 kilometers. And so this has all kinds of effects on the strength and on the viscosity and on the depletion, etc. That can be included. And so here, this is the last picture that I'll show. This is actually a similar rifted margin model that includes now this two-stage melting. And here we've actually already broken up the continental crust. We've formed new mantle lithosphere. We've formed stable 7 kilometer of oceanic magmatic crust. And here below, and this is actually the main reason for showing this, we saw this two-stage melting below the ridges shown with very small melt fractions at larger depth, and then most of the melt occurring in this melt window below between 60 and about 10 to 20 kilometer depth. Thank you.